Good morning, everybody. I feel like I should stretch or something before my 3-hour marathon here. I'd be happy with a 3-hour marathon. That's pretty fast. More like a 5-hour Oprah pace or something. Anyway, so today we're going to pick up with a discussion of state-of-the-art science results. And I've got a little bit of an outline here. It may seem like a lot, but I think it'll go pretty fast. I'm going to start with a discussion not of necessarily results, but setting the stage for a lot of the results that I'm going to be talking about. And it's a discussion of, I'll come back to that, the impact of spectral retrieval on the analysis of data and the development of that area over the last few years and how I think it's perhaps just as important as the development in our observational capabilities to obtain high-quality data. Before I do that, I forgot about this slide. There are a couple of recent reviews that I can point you towards that I think are pretty good and describe a lot of the stuff that I've been talking about and probably others have been talking about this week. A fairly recent paper, Exoplanet Atmospheres, Chemistry, Formation Conditions, and Habitability by Niku Madhusudan and collaborators, and then a slightly older paper but still quite relevant and interesting, Observations of Exoplanet Atmospheres by Ian Crossfield. Okay, like I said, I'm going to start with a quick discussion of spectral retrievals. I think Jonathan mentioned this on Monday, and I just want to reinforce and emphasize and maybe say things slightly differently than he said about how important this concept of spectral retrieval has been. And so I'm showing here a figure that I'll come back to later in the talk. This is the dayside emission spectrum of HD 209458b measured with HST WIFC3, Spitzer IRAC. And so this is observations at secondary eclipse with transit techniques. But the key thing here is that from these data, deriving the atmospheric properties and trying to read them off from the spectrum is not trivial. One thing you can say is, for example, we know that the temperature is decreasing with pressure over the parts of the atmosphere that we're seeing, but to precisely quantify that, you need detailed modeling, of course. And so the advances in spectral retrieval over the last few years have been really amazing. And so in this case, we're deriving the thermal structure of the planet's atmosphere, that's the red line, and we're quantifying our confidence intervals on that. And so that's really the key thing. I mean, for me, you haven't made a measurement unless you have a confidence interval. There's no such thing as a measured value. All that exists is a confidence interval or posterior distribution. So for HD 209458b, we derive the thermal structure of the planet's atmosphere. And more importantly, using Markov chain Monte Carlo techniques, we can account for, we can marginalize over our ignorance in the thermal structure when measuring the abundances of different chemical species, and we can also marginalize over the ignorance in the abundances when determining the thermal structure. Okay, so I'll come back to this specific result later because I want to say what this means. But I want to continue just this discussion of spectral retrievals. I've given a list of what I think is probably an incomplete list, but these are a lot of the key references that you could go to if you want to learn more about these developments. I'd say the first application really of this idea, which is coming from planetary science, was by Niku Madhusudan and Sarah Seeger in 2009. And since then, there's been a huge amount of development. You're fortunate to have one of the leading figures, Mike Line, is in the audience. He's done really amazing work. He and Bjorn Benneke, I think, are the real leaders in this area, doing truly amazing stuff. It was first applied on transits, and that's still where it sees its widest applicability. But it's also started to be used for brown dwarfs and for directly imaged planets. And then, in addition to these references that I gave here that describe a lot of the theory behind, a lot of the developments are also kind of folded into data papers. And in fact, my group has been really lucky to work with Mike Line and Jonathan and folding and incorporating a lot of those developments simultaneously with publishing data. And so you might also dig into some of the data papers. Interesting developments in spectral retrieval have been incorporated in those papers. It seems like maybe the field is just moving so fast that you just, instead of writing a paper describing just the retrieval, just gets stuffed into a data paper and you go on to the next thing. So don't think the data papers are just about the data. Okay. Okay, so the second thing I want to talk about before really diving into the science results, I want to say something about something that's very near and dear to my heart, which is this idea of high precision spectroscopy. And it's near and dear to my heart because I feel like this field has suffered, especially in the transits game, has suffered from low quality, low information content data. And that's something I've actually been working a lot over the last few years on, is to try to push that forward and obtain high precision spectroscopy. And so I want to say just a few words about that. The importance. It's probably obvious what the importance of that is, but there's some subtleties that I'd like to emphasize. And there are a few here that I'll talk about. First is when you have low quality data and low information content data, which I think are can be two separate things, the influence of your assumptions in your modeling play a big role in the outcome that you get, the result that you get. And sometimes it can be hard to trace what those assumptions are. I mean, always we're trying to be explicit about our assumptions, but sometimes there can be hidden assumptions that kind of get you. This is a figure from one of Mike Line's paper showing, I think, Mike, correct me if I'm wrong, if you make uniform priors on carbon and oxygen abundances, which seems like a very reasonable thing to do, you end up with, in effect, a bimodal prior on the carbon to oxygen ratio. You make uniform, okay, so you do a retrieval where you're trying to derive the abundances of, say, CO and H2O, and you put uniform priors on those molecules. Seems like a very reasonable thing to do. And then you get posterior distributions, and then you compute from that what the corresponding C to O ratio is. You end up effectively with a bimodal, that's the red dotted line in all three panels. The three panels just represent different quality data and doing a retrieval on that. You end up with effectively bimodal posterior distribution. And then if you have poor data or a bad marginalization scheme, you end up just getting the prior back out. And so you can think that you end up with a high C to O. C to O1, for example, is one of the peaks here. And so the point being that as the data get better, that's from here to here, and then here, the impact on the prior becomes less and less, right? So as you get very high quality data, what you had is the prior almost doesn't make a difference if it's not particularly strong, and you can get the true value. This can kind of be summed up as a quote from one of Adam Burrows' review papers, too few data points in pursuit of too many quantities, which I think is a great quote. Right, so this is like a broadband photometry. This maybe includes some spectroscopy, and this is something like a JWST observation. So you can see you have to be careful about these hidden assumptions, and they can sometimes bite you. High precision spectroscopy, you always want to be explicit about your assumptions, but high precision spectroscopy can kind of save your bacon in that situation. Yes? Yeah, Dorian.
So if you have this situation and you're in the upper left, and can you just try prior to?
Yeah, I think that's always good practice, right, is to change your priors and see if that changes the result, for sure. Yeah, I think I would say that's one of the ways. You can see one of his optimization schemes actually does deliver something close to the true answer. So you might try different schemes for that. For example, if you're just using a standard Markov chain Monte Carlo, you might go to sort of a nested sampling type algorithm to try to further explore the parameter space. I mean, that's true in any fitting situation, is you want to consider whether your local algorithm is appropriate in a global minimization problem. Yeah. Right, if the thing you really care about is the C to O ratio, you just put the C to O ratio as the parameter you're solving for, and then your uniform prior on C to O doesn't cause this problem, perhaps. Right, the problem comes again, you're solving for these molecules, but if you care about the C to O, then the uniform prior combines together to give you this funky thing. Yeah. Mike, do you remember? So it's it's a single spectrum random noise draw, and then he just fits them with different algorithms. So that's not a distribution of like it's not a Monte Carlo simulation of an observational program. It's just a Monte Carlo simulation of a retrieval for a single spectrum that's been generated. Okay, another thing that can bite you, of course, is the presence of unexpected chemical species with strong spectral features. And I love this example. This is Saturn observed as a transiting exoplanet with Cassini, Dalba et al. And you have a very high quality spectrum here, and a red and blue lines represent different models for Saturn. We should understand Saturn's atmosphere pretty well and should be able to predict these spectral features pretty well. But here is a very strong spectral feature, surprisingly corresponding with, for example, one of the Spitzer-Iraq bands. And so this is an unexpected chemical species in the atmosphere of Saturn giving a strong spectral feature. And you wouldn't see this, right? You wouldn't know that this is there if you had just broadband photometry or poor quality spectroscopy. So high precision spectroscopy allows you to unambiguously identify the chemical species that you're trying to see, and also identify chemical species that were not expected. And kind of one of the points I was trying to make yesterday is we should expect the unexpected in planetary atmospheres. All the planets of our solar system with substantial atmospheres will have a lot of unique qualities that would be difficult to predict a priori. This is sort of the unknown unknowns, which I also said yesterday, and I have to give a shout out to Jonathan for the Donald Rumsfeld figure. This morning I was like, I should try to Photoshop Jonathan's face here. So if any of the students want to do that for me, Photoshop Jonathan's face on an image of Donald, you get an A in the course if you do that, right? Okay. And then I want to say, what do I really mean about high precision data? And I want to flash back to an example a lot of people in the room might not be familiar with. This is from some of the early days of transit spectroscopy observations. This is Spitzer IRS. This is a spectrograph that's on Spitzer but no longer operational. It was only able to take spectra of two planets, HD 209 and HD 189. This is 189, spectra of 189 obtained. And this is a comparison between data taken based on just two eclipse observations. I think these are two nod positions on a slit, and then data taken with 10 eclipses. This is a slightly different instrument setup, but the real key difference is the difference in the amount of data you have here. The paper is separated by just a year, and these spectra are very different, right? And neither of the spectra obtained based on two eclipses do you see this downturn that's clearly expected from the models at 8 micron, but only shows up once you obtain a lot of data. There's a lot of art in making observations and obtaining high quality data. And some of that art is recognizing when you may have collected enough photons, but you may not have an accurate result. We're fighting a lot of times against instrument systematics that are difficult to understand. And so obtaining more data than you think you need is often a path towards convincing yourself that you've achieved a reliable result. Okay, so now I'm going to start talking about science results, and I'm going to come back to this figure that I introduced yesterday, which I just really love, showing what we know about the elemental abundances in the atmospheres of giant planets. And a lot of this talk is going to be emphasizing giant planets because those are the exoplanets that we have the most data for. And I want to home in on this problem of water in the atmosphere of Jupiter. The abundance of water is not well known in the giant planets of our solar system because these planets' atmospheres are very cold. It's condensed out of the observable atmosphere. We have a measurement of water abundance in Jupiter's atmosphere from the Galileo in situ entry probe, and it's a low number. And it's potentially explained by local meteorological effects in Jupiter's atmosphere, but this is really a big question about why that abundance is so low, if it's truly low, and if it's not low, then what is the true value? So, as I said yesterday, exoplanets offer the opportunity to study, to measure water abundances and to measure things in general that we can't measure for the solar system planets. And so this is an example of WAS-43, which I believe Laura talked about yesterday. So I just want to highlight, this for me is probably the most interesting result that I've been involved in the field of exoplanet atmospheres. And it's kind of like bog standard spectra, and that's really what's exciting to me, is that, you know, one of the first kinds of spectra that we've gotten that look a lot like the model expectations from 10, 15 years ago. We have the day-side emission spectrum and the transmission spectrum of the planet measured with HST with C3, both giving water abundances consistent with the solar, the expectation for a solar composition gas. Combining these and making some assumptions about the abundance pattern in the planet's atmosphere gives us an oxygen abundance that we can use as a metallicity proxy in the planet's atmosphere and start doing comparative planetology between the planets of our solar system and exoplanets. And so this figure, Laura must have shown this yesterday, showing the expectation for the metal enhancement, the decrease in metal enhancement in the atmospheres of giant planets as you go to higher masses. WASP-43 is fitting comfortably on the extrapolation of the trend seen in the solar system, which is truly remarkable, right? Because we're talking about metallicity estimates for the solar system planets based on methane spectroscopy. And this exoplanet, which is 2 Jupiter masses orbiting its host star with a period less than a day, and we're using the oxygen abundance derived from water, and making some assumptions about the abundance pattern and getting something consistent here. So for me, this is a really exciting result, and it points the way towards the future of what we'd like to do in this area. Continuing this story of water abundances, though, I want to offer an overview of sort of contradictory results in terms of the water abundance in giant planet atmospheres. And that's interpretation of transmission spectra of 3 hot Jupiters by Niku Madhusudan and collaborators. This is one of the figures from the paper showing the data, and then his model fits to the data. The key thing here is these features are typically smaller than what we expected from forward models before these observations were taken. And so Madhu's interpretation of these data is that this could be indicative of low water abundances. And so that was actually the statement that he made in this paper. And so here's his figure comparing the relative water abundance as a function of the planet's equilibrium temperatures, the expectation from chemical equilibrium for a solar composition gas, and then the expectation for a metal-enhanced giant planet atmosphere based on some toy core accretion model. What we see here is a couple of planets with pretty large error bars, but one planet in particular with the highest quality data, HT209, showing a substantially lower water abundance than we expect, lower than solar and certainly lower than the expectation from core accretion theory. However, I want to offer a rebuttal to this idea of a low water abundance for HT209-458b, and the rebuttal has 2 parts. One part is coming from the literature. This is a paper by Bjorn Benneke that was put out last year. It's on the archive. Here's his figure. So Bjorn looked at transmission spectra taken with HST with C3 for a number of giant planets. And so this is kind of a confusing plot. But the one I want you to look at is this dark blue line. This is his result, his model retrieval for HT209-458b. And you'll see this is a log scale. This is covering 5 orders of magnitude for his posterior distribution on water. They're both using spectral retrieval, Bjorn and Madhu. And so what's the key difference between their assumptions? The key difference is the assumptions about the presence of clouds. Madhu's retrieval was based on a cloud-free assumption, whereas Bjorn includes clouds in his retrieval and has some parameters that he uses to parameterize the cloud properties and marginalizes over our ignorance about the presence of clouds in his derivation of the water abundance. And so he gets a much larger spread in possible values and values centered on solar composition. And so this really illustrates the challenge of transmission spectroscopy with the data that we can currently get, which is that we have a limited bandpass and limited precision that we can obtain. And so there's strong degeneracies in the modeling of transmission spectra to try to retrieve molecular, absolute molecular abundances. You have the degeneracy between the pressure, the partial pressure of the absorbing chemical species, the total gas pressure, and the altitude of the clouds. Yes, Ted?
So if you look at Jupiter and
So if I'm not mistaken, there is an observation of Jupiter kind of as a transiting planet based on one of those weird solar system observations using some occultations or something like that.
Solar light off the Galilean satellite.
Yeah, right. And the result was actually surprisingly high. I think they claimed a detection actually of water in the atmosphere of Jupiter in transmission. But that's hard to reconcile with our remote observations just of direct spectroscopy and probably the in situ measurements of Galileo entry probe. And so I can't remember that reference, but maybe later if you're still interested, I could try to find that. Of water, okay. The spectrum even that I showed just a few slides ago. Yeah. Okay, so this is showing a different interpretation of the HD 209-458b transmission spectrum and showing a water abundance that's not subsolar, but with a large uncertainty. I'm coming back now to this secondary CLIP spectrum that was obtained by my group and analyzed by Mike Klein and his collaborators. It's a paper that was put on the archive just a few weeks ago. So we have a day-side emission spectrum of HD 209-458b. So this is a complementary probe of the atmosphere that should, in principle, give the same result as the transmission spectrum. And so from this, Mike derives water abundance marginalizing over our ignorance and all these other things, the temperature pressure profile and the abundance of a whole host of other chemical species. And so this is his posterior distribution here, and the dashed line is not the median of the distribution, although it could very well be. This is the expectation for a solar composition gas. And so you can see that our derived water abundance from the emission spectrum is also consistent with solar and not indicative of subsolar water abundance. So this is, for the specific planet of HD 209-458b showing probably not subsolar water abundances and consistent with this picture of WAS-43. There was a paper recently by Todorov and collaborators, including Mike Klein, where they did an analysis now not just of transiting planets, but looking at directly imaged planets, which typically have higher quality spectra than transiting planets. Now, they have higher quality spectra, but there's also, I would say, much more challenging to interpret these spectra because there are a lot of unknowns about these planets. For example, you don't know the surface gravity of the planet, so you have to derive the surface gravity and the temperature directly from the spectra. At the same time, you're also retrieving, say, the thermal structure, the presence of clouds, and the abundances of the chemical species. So this paper was focused on kappa and B, but they also pulled together water abundance measurements from a lot of different sources, and you can see them here in the caption, and plotted them. Water abundance is a function of planet temperature. There are no predictions for expectations, but, well, let's just go forward. We can just say that WAS-43b is roughly centered on the solar abundance of water. And so if you draw a horizontal line here, that pretty much represents the expectation in a solar composition gas. Now, there's transiting planets on here, and most of them have huge error bars. And so that gives us an indication of our advance for WAS-43b. This is the Medusodon result for 209, but you can say we probably moved this up because of his not including clouds in that retrieval. And then also looking at HR 8799, spectra I haven't shown yet, but results on the derived water abundance there. And so you can see here for the planets with the best data, we're obtaining solar abundances of water, which points the way towards hopefully improving the precision on the results and pushing towards being able to distinguish between Jupiter and Saturn-like enhancements in metallicities for these objects. Returning to WAS-43b, I want to emphasize this assumption. We measure a water abundance, and we try to convert that to the underlying elemental abundance. People in the solar system talk a lot about molecular abundances, and that's because in the low temperature regimes that they're dealing with, a lot of times the elements making up the molecules are almost exclusively in those molecules. So for example, I talk a lot about the water abundance in Jupiter, but what I really mean in the interesting quantity is the oxygen abundance. And this works for Jupiter because basically all the oxygen is locked in the water. The water is condensed out, we can't see it, but that's okay. So I want to emphasize the thing we really care about is the underlying elemental abundance. And so we've tried to derive that for WAS-43b, but it requires a quite strong assumption about the abundance ratios of the molecules, of the elements going into that. And the specific example of water in hot planet atmospheres relies, and using that as a proxy for the oxygen abundance, relies on the assumption of the carbon to oxygen ratio. And the reason is because in a solar composition gas at the temperatures of hot planet atmospheres, you have quite a lot of oxygen potentially locked into other molecules. CO predominantly, but potentially even CO2. And so if you're trying to make an estimate of a planet's metallicity, ideally you'd make a measurement of the complete molecular inventory of the planet's atmosphere and use that to assess the metallicity. And maybe even throw metallicity out altogether and say, what are the individual elemental abundances, like we're trying to do for the solar system. So this question specifically comes down to, what's the carbon abundance? Carbon would be the second most abundant volatile element in a giant planet's atmosphere. And so it's also considered quite important from the formation standpoint. To make this more quantitative, I show the predictions of equilibrium chemistry for a host of molecules as a function of this carbon to oxygen abundance ratio. This is for a fixed temperature and pressure, but this is representative of what you would expect in a hot planet's atmosphere. This is a bit hotter, but you can go down to 1,000 Kelvin and it wouldn't change that much. The point being that the solar carbon to oxygen abundance ratio is about 0.5. That is, you have 2 oxygen atoms for every carbon atom in a solar composition gas. Given the quantum mechanical properties of these different molecules, CO has the strongest binding energy of a molecule, and so would be the first thing to form. And so if you have more oxygen than carbon, then you have oxygen going into, leftover oxygen going into water. And so since you have twice as much oxygen as carbon, you basically, at a solar composition gas at these temperatures, get an equal partitioning of oxygen between H2O and CO. So that's represented kind of here by this intersection. The carbon to oxygen ratio, though, if you change it and you approach and even exceed 1, water abundance can change by orders of magnitude. That's because you start locking up more and more of the oxygen in CO, and there's less and less available to form H2O. Once you get to a C to O ratio of 1 and then higher, you expect orders of magnitude less water abundance. And so you can imagine if we don't have the C to O ratio of the planets right in our assumption, that we could dramatically underestimate the planet's metallicity, for example. It's unlikely that we've overestimated it strongly, because once you get below a C to O of solar, then the oxygen abundance is not increasing that much as to lower C to O ratio values. But certainly, if we had underestimated the C to O, we would dramatically underestimate the metallicity, the oxygen abundance and metallicity of the planet's atmosphere, just based on a given water abundance measurement. And so this raises the question, what are the C to O ratios of giant planet atmospheres? Well, we don't know them really for the solar system, but I emphasize that if we take the Galileo entry probe measurements at face value, the C to O ratio for Jupiter is 3. So dramatically different than the solar abundance pattern. And this has important ramifications for the formation of objects, of these objects. This is a sort of classical figure now from a paper by Karen Oberg and collaborators, showing the partitioning of different molecules, the C to O ratios of different components in a protoplanetary disk, the gas versus grain abundances, and relating that to the radial distance from the host star in terms of the frost lines of different molecules. Now, I was just having this discussion with someone yesterday. I don't think this is a prescriptive thing saying if you measure a C to O of something, it implies a formation at some location. But I think this just gives you an indication there is going to be a very different C to O ratio depending on whether you're talking about gas or grains. And the physics of the pollution and metallicity enhancement in giant planet atmospheres, I think, is not well understood. But this gives you a sense that you could expect very different C to O ratios from the host star value, depending on the formation. Mm-hmm. These are equilibrium calculations. So I think this is valuable for hot planet atmospheres where at high pressure the equilibrium, it's hot enough that equilibrium is a safe assumption. And so you're probably all familiar with this classic result for a high C to O ratio for a hot Jupiter, the hot Jupiter WAS-12b. This was a result by Niku Menadusadon and collaborators in 2011, showing here a figure from a follow-up paper by Kevin Stevenson and collaborators. The inference of a high C to O ratio for WAS-12 is based on measurements of the planet's day-side emission spectrum. There's some low-quality photometry in here, but the key thing is that you have HST-WIFC3 spectrum in the near-infrared that shows featureless spectrum, and a day-side emission spectrum, a featureless spectrum, means either the indication no chemical species that you would expect to absorb, in this case water, or an isothermal day-side thermal profile. However, there's evidence for clear absorption in Spitzer-Iraq photometry. And so this is photometry, but the ruling out of the existence of strong water absorption means that it's probably not water absorption here. It has to be the combination of other molecules. And basically, this is not the greatest figure, but basically it comes down to this is strong evidence for a high CO ratio if you take the data at face value. So for WAS-12b, I mean, this is one of the most exciting results in the field of exoplanets. This is a thing that we can't measure for the solar system planets. We're trying to do this for exoplanets, and the first one we really do this for, we're finding such a very different value from our expectations. So it's very exciting. As Laura talked about yesterday, I think, we decided to take another view of this canonical planet, WAS-12b, by taking a transmission spectrum, and the results were quite surprising. Strong water absorption features, lack of methane absorption features. Running through the equilibrium calculations, you see the water absorption that we see is too strong to be consistent with high C to O. In fact, it's quite consistent with a solar C to O. And she might have run through all these plots, but what it comes down to is we can rule out C to O greater than 1 at greater than 3 sigma confidence. I don't know if I have another figure on this. The point of this is it's not just the abundance of water, but it's the lack of absorption from other molecules that you would expect in a high C to O environment. So this assessment of the C to O ratio rests on the assumption of equilibrium chemistry, but that's probably a fairly safe thing for this hot atmosphere. And so these results were further reinforced by an independent analysis by Bjorn Benneke. I hope I made the point earlier that independent retrievals are a valuable thing because different groups are making different assumptions and things like that. And so Bjorn's analysis of our WAS-12 spectrum also is consistent with a C to O less than 1, not just consistent, but stringently favors C to O less than 1. And then he also performs this analysis on other WIFC3 transmission spectra. The key thing here is that just like for WAS-12, if you see a water absorption feature, that pretty much guarantees a C to O less than 1. Because you're seeing water, if you can unambiguously identify water, then the fact that you're seeing that and not some other molecular absorption means the C to O ratio has to be less than 1. You have to have substantial oxygen in the atmosphere that's forming water. So I think Laura's paper does a great job explaining and making this case. Bjorn's is not so great in drawing the line between the data and this assessment of the high C to O ratio, but all the assumptions are very similar. The modeling is done slightly differently, but the conclusions become the same, which I think strengthens this idea that for these hot Jupiters at least, we have no evidence for planets with high C to O ratios. And it's quite a lot of planets at this point. We can also assess the C to O ratio for non-transiting planets using high-resolution spectroscopy. So this is work coming out of Ignas Sellen's group in Leiden, who's pioneered the use of cryores on the VLT in this ground-based high-resolution spectroscopy approach. And so they had a paper led by Matteo Brogi on a non-transiting planet, HD 179949b. Who knows this planet? I guess the radio velocity folks know this planet. But the point being that with this high-resolution spectroscopy technique, they're actually able to look at wavelengths where you can see multiple absorption features from multiple chemical species, absorption features from multiple chemical species. And so they make high signal-to-noise detections of not just water, but also CO. And that starts to help break the degeneracy in your measurement of the C to O ratio. You might notice from these figures, we only set an upper limit on the C to O, because the only thing we see is water. right? So we don't actually make an assessment of the carbon abundance. We just say it has to be less than oxygen because we see water. When you actually detect a carbon-bearing molecule, that gives you a much better handle on the carbon to oxygen abundance ratio. And so they've done a really careful analysis showing the sensitivity of their data to the C to O ratio. And they actually do a cool thing, which is different than what we had done and what Bjorn Benneke had done, which is they try to derive the C to O ratio without the assumption of chemical equilibrium by simply adding up the volume mixing ratios of the different carbon and oxygen bearing molecules. And so this is really the right way to do it. Chemical equilibrium is probably a safe assumption here. It's always better to try to successively relax your assumptions and do it sort of, I don't want to say this is first principles, but just to simply make a purely empirical assessment of the carbon to oxygen ratio. Now, the high-resolution spectroscopy is super for detecting more molecules than we can with current space-based instruments. But it has strong degeneracies because you don't have a measurement of the continuum. It's a purely differential measurement doing a cross-correlation. And so you have no measurement of the continuum, and so there's quite a bit of uncertainty what the thermal structure of the atmosphere is, where you are on that thermal profile, and that sort of thing, which makes it difficult to make super precise measurements of the C to O. But
so you say they don't need to assume chemical equilibrium, and if they do a calculation assuming chemical equilibrium,
I don't. I would say it's probably broadly consistent with what they found, but I don't know that for sure. I would be shocked if it wasn't. I mean, the point is you can look at this figure. They detect water, they detect CO, they don't detect methane, which is exactly what you expect for this planet. So the detection of methane would be the thing that's kind of wonky. Mark?
I don't know what the temperature is. You also have to be a little bit careful with silicate ring in the second depth. It's about 15-20% low in silicates.
Okay.
So just nation CO.
Yeah, okay. That's really interesting. I hadn't thought of that. I don't know if we're at the 15-20% level yet, right? But that's definitely something to keep in mind. I don't know the temperature. It's probably 2,000 Kelvin, 1,500, 2,000 Kelvin. I think it's definitely. That's right. I'm pretty sure this planet is well into the safe regime in terms of temperature. It's very hot. I mean, it's a hot Jupiter, so it's 1,500 plus Kelvin, I would say. Okay. So these figures show their basically they're chi-square contours, and they're showing they have to make different assumptions about the temperature structure. So this is really the lapse rate, whether it's a steep or shallow temperature gradient in the atmosphere. I think there are also assumptions about the C to O to methane abundance ratio. So maybe they do have some assumptions about chemical equilibrium in there. Since they don't detect CH4, they only have an upper limit on that. But basically, you can see these chi-square contours dip down and are centered around the solar C to O of about 0.5. If they assume chemical equilibrium, they probably would also get a sharp cutoff at C to O1. But you can see this is, again, for a non-transiting planet using a completely different technique and a set of assumptions, evidence against very high C to O ratios. Again, for hot Jupiters. Changing gears a little bit and now talking about direct imaging, I've said the spectra for directly imaged planets are typically better than we have for transiting planets. And so here's really the classic example of that. This is a very high-quality spectrum of one of the HR 8799 planets. Really great paper by Quinn Konopaki and collaborators. This is a Keck spectrum, OSIRIS spectrum. This is an R of 4000 spectrum, which is really just fantastic, and showing absorption features of water, CO, and now an actual strong detection of methane. And so modeling done by Travis Barman for this planet and also for one of the other planets in the system in another paper, they're doing similar chi-square maps as a function of the C to O ratio. And here they're also constraining the C to O ratio to be less than 1. And interestingly, they're getting hints of a non-solar C to O ratio. And so I'd say this is really the only evidence that we have of non-solar C to O ratios, slightly higher C to O ratios, a little bit more carbon in the atmosphere than we expect for solar composition gas. Although I think the errors here are still quite large. But this points towards, this is one, I think, a definitive result. We haven't seen any planets with high CO ratios, and we've looked at a fair number already. We've looked at more planets outside the solar system than inside the solar system, right? That's cool. And then we're pointing the way towards getting, as the data improve, and for sure, I'll talk about that in the next lecture this morning, the expectations for the improvement in the data. As that improves, we're refining our techniques for extracting this really key piece of information that traces the formation of these objects. Great. So I wanted to keep going here and say, I spent a lot of time talking about the water abundance as a proxy for the metallicity and whether we can assume C to O of solar and everything. I want to give you a preview of a new result that's coming out by Kevin Stevenson, which is taking a metallicity estimate and doing it for a different molecule. So this is doing something similar as we've done for WAS43b using water. And this is again WAS43b, but doing it now for a carbon-based molecule and using that as a proxy of the metallicity. And so the data are with C3 phase-resolved spectroscopy of WAS43, and now phase-resolved phase curve observations, phase-resolved photometry with Spitzer IRAC. And so these are the spectra and the points taken at different phases, modeling of the thermal structure done by Mike Line. The key thing, though, is I'm not a big fan of photometry, but in this case, we have spectroscopy that fairly well locks down the thermal structure of the atmosphere and the abundance of water. And so assuming there are no weird molecules in the planet's atmosphere, which we can't rule out because it's just photometry, the Spitzer IRAC data are actually strongly constraining not the CO or CO2, but the combined quantity molecular abundance CO plus CO2. And so this is not the most sort of say rigorous way to estimate a metallicity, but it's just kind of a fun thing to do to see if we retrieve the total molecular abundance CO plus CO2, how does that compare, assuming chemical equilibrium, to what we expect for a solar composition gas. And so this is the figure from Laura's paper showing the water abundance recreated. Now the water abundance is shown in red, and now we have this green point which represents the metallicity estimate for CO plus CO2. And so I saw that and I just was shocked because I would never think this would work. Sorry, Mike. I never think this would work, but it agrees remarkably well with the dayside and transmission water abundance for WAS43b. Here, there's a point for the night side, but I would say ignore that in this discussion. The error bars here also, I think, slightly underestimated, and we're still working on that. But if the error bars get bigger, then the consistency will only get better. So this kind of, again, points the way towards the future. As I said, we want to take the complete molecular inventory of these planets' atmospheres, ultimately, and look at these abundances and compare them. What are their ratios? What are their absolute values? What are the predictions from the formation models for core accretion and gravitational instability and different size planetesimals and things like that? So I've been speaking about the metallicities of giant planet atmospheres, but of course a lot of work in the field of exoplanets is to push towards smaller and smaller planets. And so a big thing that's been going on in the field, say for the last 6 years, is the question of what are the atmospheres of smaller exoplanets like Neptunes and sub-Neptunes, super-Earths. And so to motivate this study of these objects, I'm showing a figure from one of Jonathan's papers from a few years ago, where he's actually trying to make predictions about the metallicities of planets' atmospheres based on core accretion model formation, and seeing how the metallicities of the planet's atmospheres would expect to be different as with mass. And so I said there's this known trend in the solar system. You go to smaller masses, the metallicity of the planet's atmospheres go up. And this model is broadly consistent with that. As you go to smaller planets, the metallicities of the atmospheres go up. There's an intrinsic spread in the distribution because of just the randomness of planet formation. There's also different expectations depending on your assumptions of planetesimal size, and there's probably a whole lot of other physics that's been, assumptions have been made about it and that could be relaxed. But this gives you the motivation. We have the solar system trend, we have this expectation from core accretion theory. What are the metallicities of the atmospheres of smaller planets? To further motivate this, I'm showing here the latest version of the mass radius diagram for small planets, transiting planets, where we've measured these quantities to fairly high precision. And I want to emphasize here that we're studying the atmospheres of these smaller planets not just to get a constraint on their formation, but to get a constraint on their actual fundamental nature. And the reason I'm not talking about this for giant planets is because when a planet becomes big enough, we know it has to be a big ball of hydrogen and helium gas. There's no way around that. But for smaller planets, we can measure the density from the mass and radius, measurements of the mass and radius, but this does not uniquely determine the interior structure and bulk composition of the planet. And so the reason is because you can imagine making a planet out of at least 3 layers, iron, rock, silicate, and now volatiles, and hydrogen and helium gas. And so when you only have 2 knowns and more than 2 unknowns, you obviously can't get a unique solution. And so we want to understand, the fundamental natures of these objects. And so the atmospheres offer a way to get further constraints on that. You can constrain your model for the interior structure of the planet if you can say something, if you can give a boundary condition about what the atmosphere is made out of. Certainly in the extreme parts of this diagram, the low density and high density planets, we know a little bit more. But a lot of these planets are in this overlapping regime of, are they rocky? Are they volatile rich? What are the masses of their gas envelopes? The quintessential example of this degeneracy in the interior structure is the planet GJ1214b, the second discovered transiting super-Earth. This is a figure from Leslie Rogers and Sarah Seeger, published right after the planet was discovered, showing the degeneracy in the interior structure models using even a fairly simple interior structure model where you have an iron core, a silicate mantle, perhaps volatile species layer, and a gas envelope. And the point is you cannot uniquely constrain the composition of the planet from just the measured mass and radius. And so this was a big thing for a while. It's kind of lost steam recently, but it was a big thing for a while to try to make an assessment of the atmospheric composition to give a boundary condition to the interior structure models. And so these were calculations done by Eliza Miller-Ricci and Jonathan Fortney, also right after GJ1214b was discovered, showing how you could have very different atmospheric compositions for the planet, and that would lead to very different spectra that should be detectable with the existing instruments. Here, we're not trying to just measure precisely the molecular absorption feature, but we're just trying to make a broad brushstroke differentiation between spectra with large features and spectra with small features. And the idea here hinges on the fact that the size of spectral features depends strongly on the scale height of the atmosphere. This is an equation that I introduced yesterday. The scale height depends on the mean molecular weight of the atmosphere. And for small planets, the mean molecular weight of the atmosphere can change by an order of magnitude. You can go, for example, from a hydrogen-helium atmosphere with a mean molecular weight of 2 in dimensionless units to something that's dominated by water or even CO2, so 20 or 40, right? So if the mean molecular weight can change by an order of magnitude, the scale height can change by an order of magnitude, the sizes of the features can change by an order of magnitude. And so that's what we were trying to do with atmospheric studies of this planet, GJ1214b, and that's really kind of the atmospheric studies of super-Earths question. I don't know, did Laura show this yesterday? She might have showed. This is a classic spectrum now, really the benchmark result for the atmospheres of super-Earths that Laura published a couple of years ago now, where we used a substantial amount of Hubble Space Telescope time to make a deep observation of the transmission spectrum of GJ1214b. And this spectrum has unfortunately come out to be completely featureless, but it's featureless at a level that's very constraining for the atmospheric composition of the planet. We rule out clear atmospheres with all sorts of high mean molecular weight compositions. And so this is one of the few definitive pieces of evidence for clouds and the existence of transiting planets. Unfortunately, it doesn't reveal what the clouds are made out of, but it's extremely constraining in terms of the cloud top pressure. So we can marginalize over the uncertainty in the cloud top pressure and rule out water abundances in clear atmospheres over a wide range of parameter space. This is the retrieval that was led by Bjorn Benneke for the GJ1214b transmission spectrum. You can see that we constrain clouds to be at very low pressures, at very high altitudes, no matter what our assumption about the water abundance in the atmosphere is. Unfortunately, this has continued to be the theme for super-Earth atmospheres albeit at less precision and less constraining. There's 436b. It's not a super Earth. It's actually a super Neptune. But still maybe in this category of smaller planets that we're trying to make assessments of the metallicity of the atmosphere. And then another super Earth, HD 97658b. So these are all HST with C3 spectra that rule out cloud-free, hydrogen-dominated atmospheres. They don't rule out clear, high mean molecular weight atmospheres. But I would say, given what we see for GJ1214b, consistency here suggests very high altitude clouds is the likely explanation here. Now there is one exception, and this is a very important and exciting exception, and that's the planet HAPP11. Its mass is about 20 times the mass of the Earth. So it's not in the super Earth regime, but it's still in this category of smaller planets. Again, HST with C3, but now we're seeing, for the first time in this mass regime of transiting planets, the detection of water absorption in the planet's atmosphere. So this is super exciting because not all of these planets have completely obscured atmospheres. Transmission spectroscopy can tell us fundamental things about the atmosphere besides just clouds, as interesting as they might be. Unfortunately, though, the possible existence of clouds, again, makes the metallicity estimate based on just this spectrum alone quite difficult. There's a strong degeneracy between the uncertain cloud top pressure and the metallicity of the planet's atmosphere. Again, this retrieval was led by Bjorn Bennicke. Basically, you have this 1 sigma contour, which is quite broad in terms of the allowed metallicities, just at 1 sigma. If you return to that figure from Laura's paper and try to put HAPP11 on it, this is what you get. So this is the red line would represent the 1 sigma confidence interval on the metallicity based on the water abundance retrieved for HAPP11. So unfortunately, the existing data are not strongly constraining, but again, it points towards a promising future for these kinds of observations. If we can make higher precision observations, perhaps over a wider range of wavelengths, we can break the degeneracy between the clouds and the molecular abundances and start populating this diagram over a range of masses. Yes? So let's save that discussion for the next lecture, because I've put that in my open questions. And maybe we can actually have a discussion about ideas on how to do that. I have one slide that's kind of like, you know, a centerpiece of this discussion. We can talk about that. I think it's a really important question. Yeah. Okay, so that's HAPP11. And then some of you may be familiar with this recent result on the super Earth 55 Cancri E. Again, HST with C3. This is a spectrum that's also not seemingly flat. And the UCL group of Giovanna Tonetti and collaborators have interpreted this spectrum to indicate low mean molecular weight atmosphere, so a hydrogen-dominated atmosphere, with an absorption feature caused by HCN. And so this is their figure in the caption. I'd say the jury is still out on the reliability of this spectrum and their interpretation of this spectrum. But again, it points towards, you know, a potentially exciting future that not all of these planets are going to have completely obscuring clouds. We should be able to make measurements and ultimately get that science that I've been talking about out of the data. Right. Right. So from the observational standpoint, which is really all I can speak to, maybe Mike has ideas about the theory too and the interpretation. 55 Cancri is the hardest target that WIFC3 has ever pointed at. And you'd be like, why is that hard? 55 Cancri is not, it's called 55 Cancri because it's a bright star, right? And that's a good thing. I hear that's a good thing. For WIFC3, though, this star is probably too bright. And so you collect a huge number of photons, but the instrument systematics depend on the photon count rate. And at higher photon count rate, the systematics are worse. And it's a doubly difficult problem because you've gathered all these photons. You think your photon limited precision should be quite good, but your systematics have gotten worse. And from what I've seen of these data, and my group has been observing 55 Cancri E not in transit with WIFC3, but in secondary eclipse, but using the same exact observing mode, and it's extremely difficult to reliably pull out the spectrum of the planet from these measurements. And we even have 4 eclipses of the planets. This was based on 2 transits. So we have twice as much data, and we're expecting to see the same planet spectrum in all 4 of these data sets. And it's still very, very difficult. Here, with just 2, I just don't feel that they can remove the instrument systematics at this level. Oops. At secondary eclipse. So it's a different, yeah, but it's essentially the same observation, right? It's the same time series observation with the same instrument, the same scan rate, same read mode, same everything, just observations at secondary eclipse. We have no idea. We may not even be able to pull out a spectrum. That's how hard it is. It may just, the whole point of that observing exercise may just be this target is too hard for this instrument. Yeah. Okay. So I also want to highlight a new result that came out for the TRAPPIST planets. This is a group of planets orbiting a planet right at the stellar-substellar mass boundary. TRAPPIST-1, this is a composite transit observation seeing simultaneous transits of planets B and C observed with HST with C3 by DeWitt and collaborators. From this double transit, they get a joint constraint on the transmission spectra of both planets. I haven't dove into this paper to see exactly how they do this, but you can imagine just a sort of hand-wavy argument. You see 2 transits, you do a composite model, and this is what you get. And so these data, these first observations of now Earth-size exoplanets rule out cloud-free, hydrogen-dominated atmospheres. I want to point out that I don't trust the statistics in this paper, and you can see why. If you look at this figure, this is where they try to derive the spectrum of just one of the planets. They say that the blue line is inconsistent at 2 sigma from these data, yet the blue line goes through the errors on all of the points, which wouldn't even be expected at 1 sigma. And so I'm a little nervous about their statistics, especially in this case, this H2O cloud-free atmosphere I don't think is ruled out at 4 sigma. This H-rich cloud-free atmosphere is probably not ruled out at 19 sigma, but you can see that's strongly discrepant. So the main conclusion from the paper is unaffected, but I'm a little concerned about how they've done their statistics here. Yeah, 300, I'd say, on the composite spectrum. The star is fainter than GJ1214, but it's also the star is a lot smaller too, so that helps in your sensitivity. Okay, but again, this is not these don't start to be definitive results, but really it's pointing the way towards the future of what we want to do. So the discussion of small transmission spectra of small exoplanets has focused a lot on the existence of clouds. And so I want to back up and go back to giant planets and talk about what evidence we have for the existence of clouds on those objects. This is a really nice paper by David Singh and Jonathan and collaborators that came out this year showing a family portrait of hot Jupiters with spectra from the optical to the near-infrared and out to the thermal infrared. And this sort of family portrait paints a picture of prevalent cloud absorption in the planet's atmospheres. And they did this really clever analysis where they looked at the ratio and the transit depth from the near-infrared to the Spitzer wavelengths, and then calculated some toy models to see what you would expect for the size of the water absorption feature at the WIFC3 wavelengths relative to this color measurement. And you can see these toy models. This is clear atmospheres with differing water abundances, and then two different prescriptions for clouds. One they just call cloudy, which I guess is a gray cloud, and then another has hazy, which is an enhanced Rayleigh scattering cloud, right? And so you can see the measurements, the individual measurements are fairly low precision for the most part, but taken as a group, they're broadly consistent with the cloudy and in particular the hazy model for these planets' atmosphere. This is further evidence against subsolar water abundances for these hot Jupiters, now in sort of statistical point of view. I like this paper for a number of reasons. I thought this is very clever in terms of creating this color versus spectral feature size, and also because it's the power of exoplanets that's still not widely used in the atmospheres game, which is the power of statistics. Right? You may ask yourself, well, if there's still so many mysteries about the atmospheres of the planets of our solar system, we should just keep studying those because we'll get a lot more data. We can actually go there and send a probe and land there and that sort of thing. But for exoplanets, we have just a power in numbers, right? And that's we can use that. And so I think this is probably the first example of that being used, and I think this is going to be an important thing to continue doing in the future. We'll never have as much data and as high quality data as we have for the solar system planets, but we have thousands of planets, right? There's a power in that. Clouds have also been indicated from measurements of hot Jupiter albedos. This is a paper by Vivian Parmentier looking at albedos, geometric albedos derived from Kepler light curves of transiting hot Jupiters, and showing the very complicated behavior of the albedos of the planets as a function of their temperatures, but then perhaps explaining that by the complicated chemistry involving different cloud species appearing and raining out as you change the temperature. This highlights how you have all these expectations for cloud species condensing out and existing for in a narrow temperature range, and then settling out of the atmosphere, perhaps being lost on the cold night side of the planet from mixing effects, and how you don't expect at all any sort of linear relationship between the albedo and the equilibrium temperature because you've got these cloud species coming in and out. I thought this was a really great paper with a model that's reproducing some somewhat mysterious results in terms of the diversity of geometric albedos for hot Jupiters. Clouds are not only affecting transmission spectra, but they could potentially affect dayside emission spectra. This is, of course, widely appreciated in the direct imaging and brown dwarf communities, where they're taking essentially, dayside spectra like we do for transiting planets and seeing the evidence for clouds. As I said yesterday, the slant viewing geometry of transits makes clouds more prominent in transmission spectra, but they could also be present in the spectra obtained with a normal viewing geometry. So this is Mike's paper on HJ209, which I showed one figure from earlier. This is another figure where he's done what I think is the first consideration of clouds in the emission spectra of transiting planets. And he found that, fortunately for this object, the presence of clouds probably doesn't have an influence. And so our conclusions about the thermal structure and the water abundance are unchanged whether we include a cloud in our modeling or not. But this is a reminder that clouds could be important in emission spectra, and especially as we go to cooler objects in the JWST regime, we want to keep this in mind. So this kind of modeling is going to be more and more important. As I said, clouds are very well known and are really dealt with in the brown dwarf and direct imaging communities. You have strong evidence for the existence of clouds in color magnitude diagrams of field brown dwarfs, and also when you put directly imaged planets on there. The well-known LT transition represents perhaps a transition in the cloud properties in brown dwarf atmospheres. And then also in the spectra of directly imaged planets, you see evidence for clouds. I think I just have one figure from one of Andy Skimmer's papers showing the interpretation of data for HR 8799, some photometry and spectrophotometry for this planet, and how it can only be reproduced really by models that include clouds. I'm not really an expert on this, so I'm just going to leave it at this. But certainly you have a lot of experts in the room right now and as the workshop continues. Mark Marley and Andy Skimmer and others. Just as a sort of break here in the middle,
I want to share with you an email conversation I had with Kevin Zonla. I was reading Kevin's and collaborators' paper talking about hazes on 51 Area B, one of the new directly imaged planets, and I was struck by this shocking sentence here, talking about different possible cloud and haze particles. The familiar candidate is an organic photochemical haze, loosely analogous to the hazes seen over Titan, yeah, Pluto, yeah, or Beijing. What doesn't fit in this list of 3? So I sent an email to Kevin. I said, if I was the kind of person to tweet, I would have posted this last night, only to the imaginative minds like Zonla et al. Are Titan and Pluto as accessible as Beijing? And Kevin wrote back, to a NASA employee, Titan and Pluto are more accessible than Beijing. And then referenced this news article talking about the restrictions from federal government employees and collaborating with the Chinese. And so, man, Exoplanets is a lot of fun, right? There's a lot of characters out there, and we can have a lot of fun with this stuff. Anyway, okay. Am I getting tired, or is it just me? Yeah, anyway. So we got another 20 minutes to go, and I think I'll get through these slides. Changing gears again, going down my laundry list of stuff that I'd like to talk about, I'd like to talk a little bit about the idea of non-equilibrium chemistry. This is something we've already talked about a little bit, and I've said, don't worry about it, everything's in equilibrium, we measure the water abundances and everything's just hunky-dory, but everything might not be hunky-dory. You could have evidence for non-equilibrium chemistry. And so that's actually been a question that's been around for quite some time in the transiting game, because some of the early measurements of photometry and spectra were not reliable, but people thought they were good. And so they started doing analyses and modeling, and they got wonky molecules completely inconsistent with the expectations for chemical equilibrium. And so it was a big thing some time ago, and this is, I think, fallen a little bit out of favor, but hopefully it comes back as the data start to improve, this idea of measuring molecular abundances with modern retrieval techniques and trying to assess whether you're in equilibrium or not. This is a figure from one of Mike's papers from his thesis, I think, plotting the equilibrium constant for the, this is showing the balance between the partial pressures of methane, water, and CO, plotting this equilibrium constant, which depends on the Gibbs free energy, as a function of temperature, and plotting the empirical measurements of the equilibrium constant as determined from the abundances of those chemical species measured in the atmosphere versus the expectation. And so you can see here, for most transiting planets, the error bars are large and you're consistent with chemical equilibrium. And a lot of these data, this is somewhat dated now because the data have gotten a lot better over the last couple of years from HST with C3. And so you could redo this plot, but probably for most of these planets it would be very similar. But there are a couple of planets stick out in terms of being evident for disequilibrium chemistry, and in particular for our measurement of low methane abundances. GJ436b, a transiting planet, and this inference is coming from secondary eclipse photometry. And then HR8799b, one of the directly imaged planets, so this is a directly imaged measurement. So for GJ436b and HR7, well, I think for 436b, there's a complete absence of methane seen in the spectrum of the planet. For the HR8799b, there's methane detected, but a very low abundance. And so this could be evidence of mixing and quenching of CO and CH4 from deep inside the planet's atmosphere. Whew, no questions about that. Moving on to sort of more indirect evidence for non-equilibrium chemistry, I think the spectrum of the transmission spectrum of GJ1214b, its extreme flatness and featurelessness, which indicates clouds at very high altitude, is perhaps indicative of photochemistry happening in the planet's atmosphere. This is a figure from one of Caroline Morley's papers showing models where they try to reproduce the featurelessness of this spectrum using different cloud models. And for me, the one that seems most believable is the cloud model based on photochemical haze production rather than equilibrium condensates. And so this is the figure from that showing how you really, even in this photochemical regime, you have to have a very high, I think this is a conversion factor from the photochemical precursors to hydrocarbon soot. If I'm right, this F factor is that conversion factor, right? And so this is more indirect evidence than actually measuring, for example, the methane abundance of non-equilibrium chemistry. But this could be, perhaps the first evidence, the first real hint of photochemistry influencing the abundances of chemical species in exoplanet atmospheres. Changing gears again, we're going to talk about the thermal structure now. And I introduced this topic by referencing back to the thermal structures of the atmospheres of planets in the solar system. Here's Earth's thermal structure, which is extremely important for our existence, and the thermal structures of the planets, the giant planets. An interesting common thread between these thermal profiles is the existence of thermal inversions. That is, as you move up in the atmosphere, the temperature decreases till you reach the point which you might call the tropopause, and then there's an increase in temperature to higher altitudes. The existence of thermal inversions in the atmospheres of our solar system planets is caused by the irradiation from the sun and the existence of chemical species that are absorbing shortwave radiation from the sun and heating the atmosphere. Thermal inversions were considered for exoplanets and even thought to perhaps exist. Some of the first Spitzer photometry measurements of the spectral energy distributions of transiting hot Jupiters revealed some anomalous results that were perhaps attributable to thermal inversions. The classic example is the day-side emission spectrum for HD 20945AB, measured just in photometry, which is tricky. But the ratio of the 4.5 to 3.6 micron channel, where the 4.5 micron is showing a deeper secondary eclipse than 3.6, is indicative. This should be an absorption band, and if the absorption band goes up, the temperature has to be higher in the atmosphere. So that's this green line. So this was first proposed by Heather Knudsen, Adam Burrows, and collaborators in a couple papers from about 9 years ago. And then this figure is from Madhusudan and Seeger, showing a retrieval of inverted thermal profile based on these data. So the thermal inversion was formally only about a 2 sigma result, taking the Spitzer IRAC photometry at face value. But still, it was a very persistent idea that led a lot of people to propose that as an explanation for some weird data that they got for other planets, and proposed, it motivated theorists to look for chemical species that could be causing the thermal inversion. It motivated people to try to understand why some planets would have it and some planets didn't. And it motivated observations at other wavelengths to look for the absorption signature, say, in the transmission spectra of these planets to find that chemical species. So my group had done a couple of papers now on HD 20945AB. First, we reassessed the Spitzer IRAC points and found that some of them changed dramatically based on newer observations, better observing modes, and better data reduction techniques. And then the real ultimate thing is to get a spectrum of the planet, so a WISD-3 spectrum of the planet. Again, this is day-side emission. And so putting this together, you see in the spectrum, and this is really the power of spectroscopy, right? This is the clear, unambiguous absorption feature of water. So you can say, just from reading this off the figure, water is present in the atmosphere in substantial amounts, and the temperature decreases as you go to lower pressures over the part of the atmosphere that you're seeing. You just read that off the figure. Doing the retrieval to quantify that, you get this thermal structure, which is inconsistent with a thermal inversion at very high confidence. So thermal inversions not existing in 20945AB, the original planet that this was proposed for, and really set this a whole area of investigation into motion. This has also been confirmed and consistent with measurements from the ground based on high-resolution spectroscopy. This is a figure from Henrietta Schwartz from Ignace Sellen's group using CRIRES at the VLT. They were not able to make an unambiguous detection of absorption in the planet's atmosphere that would be consistent with no thermal inversion, but they were able to rule out the strong thermal inversion that had been originally proposed. The point being that if you have this strong white, yellowish white, that represents a sort of a hit. You're playing Battleship. It's like hit, 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 miss, right? You miss with a strong inversion. And so that's not detected and ruled out. But they can't distinguish between narrow, broad absorption and a weak inversion. Whereas with our data, we can. But this is really, really nice that we get these consistent results for the same planet with very different techniques. We can compare this to the predictions of 1D models. And so I think this is really exciting. We calculate some 1D models with Jonathan's code with different levels of redistribution, the black lines, and see that our retrieved model, whether we include, this is which version of this? Well, there's two versions of the parameterization for the TP profile, and it's consistent with some intermediate redistribution factor. You see the slope and the change in this is very similar to the prediction from the 1D radiative convective model. So this is suggesting a reality that we're actually seeing, which is comforting. Thermal inversions are not dead, though. Recently, there have been a series of papers for super hot Jupiters, suggesting the possible presence of inversion or the chemical species that could cause inversions. Here's a spectrum of WAS-33b. This is a planet with an equilibrium temperature of about 3,000 Kelvin. So this is approaching stellar temperatures for the planet. The WIFC3 spectrum ends, this is a ground-based point, and there's some Spitzer data and another ground-based point, suggest weakly, in my view, the possible existence of an inversion. To me, the WIFC3 spectrum looks like a black body, which is actually consistent with what I see for other hot planets. I think I have a slide on that coming in a second. And it's really this one photometry point that's driving this idea of an inversion rather than just an isothermal atmosphere. But still, this is a very different temperature regime than H2209, and so it's not unreasonable to expect that a very different kind of thermal structure for the atmosphere. So the thermal inversion idea has maybe, has morphed into something else, and it's still out there. Now, in terms of detecting the chemical species that could give rise to that, this is what I mean. WAS-121, again, an HST WIFC3 spectrum. This shows water absorption, but if you combine with some, again, ground-based photometry, you have the possible existence of TiO. TiO is one of the chemical species that was thought to potentially cause thermal inversions. And so it'll be interesting to see what the day-side spectrum of this planet looks like, and higher precision data here in the optical to actually see, to tell us whether we expect, we are actually seeing TiO, which would be a first in this planet. And this is a very hot planet again. It's very different from HT209. Some of the data from my own group have suggested the possible existence of two classes of highly irradiated thermal structures in planet atmospheres. For WAS-43 and 209, which I've talked about a lot, we see this clear absorption signature of water. But for WAS-12 and unpublished data for WAS-103, and also not shown on here, WASP-18, much hotter planets, we see what look to be, at least over the WIFC3 bandpass, isothermal black body-like spectra. And so I think one of the open questions is trying to reconcile the differences that we're seeing between these really hot planets and the sort of cooler, more canonical hot Jupiters in terms of their thermal structures. My understanding that theoretically it's very difficult to get a perfectly isothermal atmosphere, and so I think this is an interesting theoretical challenge if the data continue to show this sort of divergence, and in particular this phenomenon, the hottest hot Jupiters. Let's see how many more slides I have. So I'm going to talk about, so let's talk about this. Almost done. Evaporation. So changing gears to evaporation. So this is not something that I've worked on, and so I'm doing my best to try to capture what's going on in the literature. Planets that are very close to their host stars obviously are very highly irradiated, and the high irradiation could be driving mass loss from the planets. This is a figure from a paper from David Ehrenreich and Jean-Michel Desert from a few years ago, looking at the population of transiting planets and calculating the expected mass loss rates for the planet. Now, it's interesting to point out, of course, that this has been observed. The actual ongoing mass loss of hot Jupiter atmospheres has been seen. The classic result is for HT209, observations at Lyman alpha, where you see a clear dip in the Lyman alpha absorption between before and then during transit. Lyman alpha is tough because it's absorbed strongly by the interstellar medium. So that's the core here. And it's also, there's some geochronal effects on this line too that make the measurements quite difficult. But if you have a star that has a significant red or blue shift from the Earth and thus has the Lyman alpha shifted from the Earth's point of view, then you can move this Lyman alpha out of the ISM absorption and then measure either in the wings or perhaps even see the core this absorption. So 209 is a hot Jupiter that's been observed this way, and then also recently there was a paper by David Ehrenreich and collaborators for the hot Neptune GJ436b, and this is a really stunning observation. The absorption on 209 was quite large, but was still only a few percent. Now we're talking about 436b. The transit of 436b is on order of tens of percent, right? So this is suggesting the presence of a huge cloud of neutral hydrogen streaming off the planet in this, and they're making this theoretical prediction. This is a theoretical prediction of how this cometary tail of neutral hydrogen is just streaming off this hot Neptune and causing this huge dip in transit, much larger than the transit seen just for the planet itself. So obviously this is an exciting thing. The idea of evaporation is probably going to become more and more important as we move to smaller planets. Hot Jupiters aren't seeming to be losing substantial mass, and so it's really kind of in the details. But the whole evolution of smaller planets could be dramatically affected by mass loss. And so further measurements in this area are expected and will probably be very interesting. So how about we stop here, and I have a few more slides to go in this lecture, but I think people are losing focus. I'll pick back up after a 30-minute break. That's okay. I'll pick back up here after a 30-minute break. I'll finish this summary of observational results, science results, and then I'll start talking about expectations for future facilities and instruments. Okay, so I take my speaker's privilege and say 30-minute break. And obtain high-precision spectroscopy. And so I want to say just a few words about that. The importance. It's probably obvious what the importance of that is, but there's some subtleties that I'd like to emphasize. And there are a few here that I'll talk about. First is when you have low-quality data and low information content data, which I think are can be two separate things, the influence of your assumptions in your modeling play a big role in the outcome that you get, the result that you get. And sometimes it can be hard to trace what those assumptions are. I mean, always we're trying to be explicit about our assumptions, but sometimes there can be hidden assumptions that kind of get you. This is a figure from one of Mike Line's paper showing, I think, Mike, correct me if I'm wrong, if you make uniform priors on carbon and oxygen abundances, which seems like a very reasonable thing to do, you end up with, in effect, a bimodal prior on the carbon to oxygen ratio. You make uniform, okay, so you do a retrieval where you're trying to derive the abundances of, say, CO and H2O, and you put uniform priors on those molecules. Seems like a very reasonable thing to do. And then you get posterior distributions, and then you compute from that what the corresponding C to O ratio is. You end up effectively with a bimodal, that's the red dotted line in all three panels. The three panels just represent different quality data and doing a retrieval on that. You end up with effectively bimodal posterior distribution. And then if you have poor data or a bad marginalization scheme, you end up just getting the prior back out. And so you can think that you end up with a high C to O. C to O1, for example, is one of the peaks here. And so the point being that as the data get better, that's from here to here, and then here, the impact on the prior becomes less and less, right? So as you get very high quality data, what you had as the prior almost doesn't make a difference if it's not particularly strong, and you can get the true value. This can kind of be summed up as a quote from one of Adam Burrows' review papers, too few data points in pursuit of too many quantities, which I think is a great quote. Right, so this is like a broadband photometry. This maybe includes some spectroscopy, and this is something like a JWST observation. So you can see you have to be careful about these hidden assumptions, and they can sometimes bite you. High precision spectroscopy, you always want to be explicit about your assumptions, but high precision spectroscopy can kind of save your bacon in that situation. Yes? Yeah, Dorian.
So if you have this situation and you're in the upper left, and can you just try to prior to?
Yeah, I think that's always good practice, right? Is to change your priors and see if that changes the result, for sure. Yeah, I would say that's one of the ways. You can see one of his optimization schemes actually does deliver something close to the true answer. So you might try different schemes for that. For example, if you're just using a standard Markov chain Monte Carlo, you might go to sort of a nested sampling type algorithm to try to further explore the parameter space. I mean, that's true in any fitting situation. Is you want to consider whether your local algorithm is appropriate in a global minimization problem. Yeah. Right, if the of HD 209458B measured with HST WFC3, Spitzer IRAC. And so this is observations at secondary eclipse with transit techniques. But the key thing here is that from these data, deriving the atmospheric properties and trying to read them off from the spectrum is not trivial. One thing you can say is, for example, we know that the temperature is decreasing with pressure over the parts of the atmosphere that we're seeing, but to precisely quantify that, you need detailed modeling, of course. And so the advances in spectral retrieval over the last few years have been really amazing. And so in this case, we're deriving the thermal structure of the planet's atmosphere, that's the red line, and we're quantifying our confidence intervals on that. And so that's really the key thing. I mean, for me, you haven't made a measurement unless you have a confidence interval. There's no such thing as a measured value. All that exists is a confidence interval or posterior distribution. So for HT 209458B, we derive the thermal structure of the planet's atmosphere. And more importantly, using Markov chain Monte Carlo techniques, we can account for, we can marginalize over our ignorance in the thermal structure when measuring the abundances of different chemical species. And we can also marginalize over the ignorance in the abundances when determining the thermal structure. Okay, so I'll come back to this specific result later because I want to say what this means. But I want to continue just this discussion of spectral retrievals. I've given a list of what I think is probably an incomplete list, but these are a lot of the key references that you could go to if you want to learn more about these developments. I'd say the first application really of this idea, which is coming from planetary science. Good morning, everybody. I feel like I should like stretch or something before my 3-hour marathon here. I'd be happy with a 3-hour marathon. That's pretty fast. More like a 5-hour Oprah pace or something. Anyway, so today we're going to pick up with discussion of state-of-the-art science results. And I've got a little bit of an outline here. It may seem like a lot, but I think it'll go pretty fast. I'm going to start with a discussion not of necessarily results, but setting the stage for a lot of the results that I'm going to be talking about. And it's a discussion of, I'll come back to that, the impact of spectral retrieval on the analysis of data and the development of that area over the last few years and how I think it's perhaps just as important as the development in our observational capabilities to obtain high-quality data. Before I do that, I forgot about this slide. There are a couple of recent reviews that I can point you towards that I think are pretty good and describe a lot of the stuff that I've been talking about and probably others have been talking about this week. A fairly recent paper, Exoplanet Atmospheres, Chemistry, Formation Conditions, and Habitability by Niku Madhusudan and collaborators, and then a slightly older paper, but still quite relevant and interesting, Observations of Exoplanet Atmospheres by Ian Crossfield. Okay, like I said, I'm going to start with a discussion, a quick discussion of spectral retrievals. I think Jonathan mentioned this on Monday, and I just want to reinforce and emphasize and maybe say things slightly differently than he said about how important this concept of spectral retrieval has been. And so I'm showing here a figure that I'll come back to later in the talk. This is the dayside emission spectrum. Was by Niku Madhusudan and Sarah Seeger in 2009. And since then, there's been a huge amount of development. You're fortunate to have one of the leading figures, Mike Line, is in the audience. He's done really amazing work. He and Bjorn Benneke, I think, are the real leaders in this area, doing truly amazing stuff. It was first applied on transits, and that's still where it sees its widest applicability. But it's also started to be used for brown dwarfs and for directly imaged planets. And then, in addition to these references that I gave here that describe a lot of the theory behind, a lot of the developments are also kind of folded into data papers. And in fact, my group has been really lucky to work with Mike Line and Jonathan and folding and incorporating a lot of those developments simultaneously with publishing data. And so you might also dig into some of the data papers. Interesting developments in spectral retrieval have been incorporated in those papers. It seems like maybe the field is just moving so fast that you just, instead of writing a paper describing just the retrieval, just gets stuffed into a data paper and you go on to the next thing. So don't think the data papers are just about the data. Okay. Okay, so the second thing I want to talk about before really diving into the science results, I want to say something about something that's very near and dear to my heart, which is this idea of high precision spectroscopy. And it's near and dear to my heart because I feel like this field has suffered, especially in the transits game, has suffered from low quality, low information content data. And that's something I've actually been working a lot over the last few years on, is to try to push that forward.